Hi, we're with Siva Sivaram, the CEO of Twin Creeks Technology. They've just come out with a very interesting new design for making solar cells. Siva, can you sort of explain the problem that you guys faced in developing the Hyperion machine?
Sure. So, solar today, obviously a very important industry, about 23 gigawatt installed capacity, but it's not growing. It's not growing this year because the prices have collapsed.
Right.
The prices have collapsed to an extent that you can today get a watt of solar panels for about 85 cents.
Mm-hmm.
So 85 cents a watt, the solar panel maker actually makes no money. Its margin is in low single digits. In that 85 cents, about 60 to 62 cents is incoming materials. About 40 cents of silicon, about 5 cents of glass, about some aluminum, some silver paste, some backsheet. You put all of that out, about 62 cents is incoming materials. You have 60 cents of incoming materials, the product sells for 80 cents. There is no room for any improvement.
You can't build a business doing that.
Exactly.
Yeah.
There is no value addition inside that factory. Something comes in, something goes out with no value addition.
Okay.
We looked at this 40 cent of silicon, which is 50% of the cost, and said, what can we do to reduce that cost? So we used a technology called proton-induced exfoliation, PIE. Proton-induced exfoliation is a powerful technique where any single crystal material, monocrystalline material, you shoot a beam of protons, which are really hydrogen ions. And depending on the energy with which you shoot these ions at the surface, they go lodge themselves behind the surface. And higher the energy, the deeper they go.
Mm-hmm.
And if you put enough of them, they form little micro bubbles of hydrogen. You heat it, you heat that substrate, the top layer just peels off. So using that, we went back and looked at how much silicon do you really need to make a solar cell? Efficient solar cell.
Right, and this being the most of the cost of a cell.
50% of the cost of the cell comes from the silicon.
Right.
You're wasteful today in using the 200 microns. If you take a wafer and you look at it, it is opaque. All the light is not going through.
Okay.
Right? You go back and say, how much do you really need? We said, we did the studies, we said we could do it with about 20 microns.
Right.
And when you make a 20 micron cell, how we can make the good high efficiency solar cells, but you now cut the cost substantially. You're doing 1/10.
Right.
You're using 1/10 the silicon that is being used by the traditional makers.
Siva, you should show us the
So what you get out of it is a solar cell that looks like that.
Right.
So here is a solar cell, crystalline silicon using proton-induced exfoliation. Not only is the cell thin, light and flexible, but it's also very strong.
Right.
It does not break.
Right.
The thin silicon, surprisingly, is very flexible, and with the metal backing in the back, you now have a very strong, very flexible and low cost solar cell.
Mm-hmm.
So you take those solar cells and you can make a module. So I'm showing a 4-cell module. Usually you'll have a 60 or 64 cell module on top of your roof.
Right.
Look at how flexible it is,
Yeah.
how lightweight it is. And it's also makes the materials to be more productive. That same 60 cents that you got out of it, you don't need that much to make this. You use less than 10 cents for the silicon instead of the 40 cents.
And you're eliminating the glass.
You're eliminating the glass, you're eliminating the aluminum, you're eliminating the backsheet, you're eliminating the weight.
Yep.
So there is no concrete reinforcement that you need, you don't add steel on it.
Yeah.
So every step of the pathway, down the supply chain, you remove the waste, you make the material more productive, you add more value in your factory where you are making this solar cell instead of just taking materials and selling it for a few cents more.
Yeah, okay.
So that's the technology that drove the building of this machine. So where is the value here? The value here is in the ability to make those thin lamina.
Right.
And how do you make the thin lamina? You use the Hyperion, which is the big machine, the accelerator that is used for producing.
And the plan is to manufacture them in the U.S. at a plant near, I guess,
Mississippi.
in Mississippi.
So to make it even more, the technology is uniquely U.S.
Yeah.
the technology for making these accelerators, that the Hyperion, is developed in the US. It's a skill that largely stays within the United States.
Right.
It was something that has grown over time in the US, and it is not something that can be easily copied.
Right. Right.
So we have built the machine here, we'll continue to make the machines here, but of course making the cells and panels is a very, very competitive, very, very
Right.
labor intensive.
Right. It's not an area where the U.S. can really compete anymore,
Exactly.
right?
It is not an area where US can
So,
really compete anymore.
so the sweet spot for you guys is in adding value, innovating, sort of taking different technologies, putting them together in a unique way, right?
Precisely.
Yeah.
Precisely. So the accelerator technology existed before. We adapted it to this application. We had to invent some things new to make this happen.
Right.
So with that little bit of invention on top of the existing infrastructure that exists around the US, we have created a brand new application
Right.
for a technology.
Yeah. And a very strategic market for the
And
U.S.
it is a very important worldwide market.
Yeah, and so you've had some interest in the Hyperion in China, you said, right?
Yeah, so we have been now, since the product was introduced several weeks ago, we have started going around the world, and we are starting to qualify and put in customers.
Right.
The first time we were in China several weeks ago, we saw a lot of interest. Now we have about 5 customers that we are now
Right.
qualifying and figuring out how to get these machines into
Right.
their sites.
Right. But from a manufacturing standpoint, the key here is that the IP and the manufacturing of these machines
The
stay in the
know-how
US.
stays in the US.
Right. Right.
And
right.
this is where we will make it, and this is where we will continue to spend more R&D dollars to make these machines more productive year after year after year, so that manufacturing and the skills stay in the US.
Great. Okay. Siva, thank you very much for your time.
Welcome, George.